Hello folks, we should have built this model in class, but I wanted to go over it one more time, or in case we don't get to it in class, I want you to have this and I want you to have this structure. And so we have this simple population model that you can download, and you should run it, and you should play around with the birth rate and with the average lifespan. In class, I'll talk about how you can switch that average lifespan to a fraction if you want it by taking the reciprocal. And right now what I want to do is I want to add in a carrying capacity that will be capable of generating S-shaped growth in this system. We're arguing that structure, the feedback loops in these systems and the stocks and flows are generating the type of behavior we're observing, and we know that in a lot of natural systems there is a carrying capacity and that there is ideally S-shaped growth, and that's what I'm going to build now. I'm going to go up to my converter and click on that and come down, and I'm going to type in carrying capacity. And this is some physical limit. And this is a simple way of doing it, but let's keep it simple for now. So I have a carrying capacity. And the carrying capacity is how large my human population up here can grow. Let's assume that we're on some type of island, and there's going to be a limit to how many people the island can support. And I'm going to go down in here, and I'm just eyeballing this. I'm going to say I'm going to limit it at 450. So I'm going to double click on this, and this is going to be a constant for now. So I'm just going to type in 450, and this is carrying capacity, but for now the people are going to be the units. I'll go up and click to my converter, and I'm going to click on my converter, and come down and put a new variable in here. And this is going to be the ratio of population to carrying capacity. And again, I'm trying to give these variable names that if anyone was looking at this, they could figure out the equation. And you should just take a moment, stop the video, and think about this. What's this equation going to look like? I'm going to go, and there's going to be a connection or information from my population going into my ratio, and there will be also information from my carrying capacity going into my ratio. And now I have to figure out the equation for this. And I've been saying that the equations are, at this point, it's simply, addition, subtraction, multiplication, and division. And just the name of this, the ratio I know I'm going to be doing division of population to carrying capacity. So population will be in the numerator, and I'll put a division sign in here, and carrying capacity will be in the denominator. Whoops, let me double click on that. I clicked on the wrong variable. I got to go up here into my required inputs. One other thing I will show you, there's something about safe division. If you've done any computing, you know you have runtime errors. Like if I put carrying capacity at 0, this would give me a runtime error. What I can do is, if I had a double division line in there, it's telling the software, do safe division. So if for some reason I crank carrying capacity down to 0, the model would still run. My ratio would actually just be 0 at that point. So that was a little of a side. So what are the units here? So population is in people and carrying capacity is in people. And if I am dividing population by carrying capacity, then this should be dimensionless. The people are canceling out. So dimensionless. And now let's just think, what should this look like? So I'm starting out, this is 400, and I've got 100 divided into 450 actually. So this should, my ratio should start out a little above 0.25. But my population is growing sort of unconstrained here over this 100 years up to 500. So it's going to be greater than carrying capacity. So this ratio would end up being greater than 1. So let's simulate this. And now what I can do is I'm going to click on my ratio of population to carrying capacity, and I'm going to go up here to my explore results, and I'm going to click on that. And this gives me a quick graph, and it gives me the actual output. And I can see what the numerical values are. I'm starting at a 0.22. So, and that's correct. My mental model was wrong. If I was going to be above 0.25, it's going to be below because it's 100 divided by 450, not 100 divided by 400. So that makes sense. And it's growing because my population is growing, my numerator is staying the same. And it does end up a little bit above 1. because it went to 500, about 10% more. So I'll close that. And now what I want to do is add some feedback. And the idea that as I'm reaching my carrying capacity, this ratio could have an effect on births. And I'm going to add a variable in here, and this is going to be a nonlinearity. And I'm going to name this the effect of the ratio population on births. I'll go up to my connector, and I'm just going to connect my ratio to this. And the ratio is the only thing coming in. This will be a nonlinearity. I'm going to click on ratio and put it in my required inputs. There's only that ratio coming in, so this should be dimensionless. And I'm going to click on this graphical function here, and this is what's new. I'm going to click on the graphical function. I'm going to go click on a graph, and as a default, it's going to give me this. And so this is a nonlinearity. This ratio is going to be the inputs, and I can have changing outputs based on these changing inputs. And I'm going to say we have a hard carrying capacity. So I'm going to make this 1. And as this ratio reaches 1, so if you think about this, as the population is growing and approaching the carrying capacity of 450, this ratio is going to start to approach 1. And as it approaches 1, it'll have an effect on the ratio of bursts. So I'm going to take this and bring it into the burst and multiply up there. So if I multiply by a number that, if this is 1, when I multiply up here, it simply means that this would be 1, and the model would continue on as it had before. If I multiply by a number, if this I allow to become greater than 1, then I'll be multiplying by a number greater than 1. My bursts will be increasing. My population will be growing faster. And if I multiply by a number less than 1, I'll be slowing down my births, and they will not be increasing as fast. And if you think about it, if we're say when this reaches carrying capacity and this ratio is 1, if this is a hard limit, then what should be happening is I should be controlling my my burst should be really going to 0, basically, is what it is, right? If it's a hard limit, as I approach that 450, I should not be having any more bursts if this is a hard limit. So I'm going to, let me get a little lost. I'll double click on the effects again. And I can click on the points here also, and I could type in numbers. One of the things I can type in the numbers here, or I could pick one of these graphical functions from below. I'm going to go back to my graph, and let's think of what the story is that I'm telling. When it's 1, it should be very low. And if I'm not near my carrying capacity, perhaps I could have bursts at a number greater than 1. So I'm going to pick this negatively sloped S-shaped decay graph. And you can see this is the 1 point. So when I am halfway to reaching my carrying capacity, that's when it will be 1. When I'm above halfway to my carrying capacity, I'm going to be saying that I'm going to have fewer and fewer bursts as I approach this capacity. So I have now made this nonlinear function that I've included in my model. I'm going to click on the connector. I'll go up and connect it to bursts. Double click on bursts, and this is just going to be a multiplication by the effects. And I don't care about the order of operations. It's going to be from left to right. It's not going to matter in this case. I'm going to click OK. Let me get rid of this. And let's simulate and see what happens. So one of the things you should be asking is, how do you think this is going to change? Let me do one more thing. I'm going to click on this, and I'm going to hold my Command key on the Mac and just drag in this variable. And you can see there is my carrying capacity. This is a hard carrying capacity, so I'm going to anticipate that there's no way that my population, that blue line, should be capable of going above that red line. I'm going to simulate now, and there you go. This is S-shaped growth now, and it's below the carrying capacity, and it's much below. So this is one of the things I'm going to ask you to figure out. Why is there a gap between these two? And I will tell you that this is called a steady state error. I do not approach the gap, or that this gap is not being closed. So I think that's let me add one more thing. Let's say that as the population approaches the carrying capacity, that people are going to start starving and that deaths would increase. So I could add another nonlinear function into here. So I'm going to click. And again, when it's a nonlinear function, I type effect. And that way, when I'm looking at my models, I know if I see an effect, I have a nonlinearity in there. So it's the effect of population on deaths. And it's going to be very similar to the model or to the structure I used before. I'm going to connect my ratio to the effect, and let me connect the effect to the deaths. If I go in and do deaths first, I want to make sure I'm doing my division first. So I'm going to put parentheses around this, and then I'm going to multiply by that effect. And that should be good. The unit should be correct. It indicates that I don't have one invalid equation. I haven't calculated this yet. I'm going to double click. It has to be equal to the ratio. The only thing coming in is that ratio, which is dimensionless, so this should remain dimensionless. And now I'm going to click on the graphical function. And again, I think, click on the graphical. I think I want to have a hard limit, so I'm going to make this 1 again. And the question is even if I'm picking one of these down here, what do I want the slope to be like should be the first question. So as I am approaching 1 here, as my population is increasing and approaching my carrying capacity, that ratio will turn to 1. How do I want that to have an effect on deaths? So as it approaches 1, the carrying capacities, deaths should probably increase, and my argument is that starvation is occurring, crowding could be occurring, that their disease could be occurring, that there are more things occurring that are going to increase death. So any number on the scale from 0 to 2 that is above 1 would increase my deaths because I'm multiplying in there. So I would want a slope that has a positive slope. And I'm going to select this S-shaped here is what it is. And one of the things I'm betting is that there's no way that deaths will go to 0 even if there wasn't much carrying capacity. I'm going to go into the points, and I'm just going to have a small 0.01. There always has to be death, I believe. And so I have done that, and now I'm going to simulate. All my units are correct. And before you simulate, you should always ask, you're testing your mental models, what do you think is going to happen? Will this be closer or farther apart than it was before? I'm going to argue that there's going to be probably no real change. I could be wrong. Let's see. I think it's slightly lower is what it is, even though I've added that second nonlinearity. And so again, the question is why do we have this steady state error, this gap between the actual carrying capacity and what the population ends up being? And if you think about it in sustainability terms, this is probably a pretty good thing, that there is a gap between this. So if we did something that increased the population, if I increase the birth rate, it's happening sooner and I'm getting a little bit higher and I'm starting to close the gap, but I never reach there. I think if I overshoot my carrying capacity, there's a possibility of a collapse occurring. So again, question for you folks to answer is, why is there a steady state error in this model? And is it realistic to what happens in the real world? And again, we'll be discussing this stuff in class, and I'm anticipating you would watch this video after class as reinforcement. Thanks, and I will be seeing you.